Okay, so welcome everybody to this seminar. Hi. Well, today is a pleasure to have Davide Coluccia. Davide is a PhD student at Bocconi University, but currently he's visiting the Center for Economic History at Northwestern University, if I am right, no?
Right.
Okay, so he's presenting today Religiosity and Science, an Oxymoron, Evidence from the Great Influenza Pandemic. So yeah, Davide, you can share your...
I think I cannot at the moment.
Oh, let me, yeah, let me change now. Try now, please.
Yeah, now it should work.
Okay.
Great. Can you see my slides?
Yes. So the seminar lasts for 1 hour with questions included. Okay, so the floor is yours.
That's great. Thank you very much. I'm very happy to be presenting this paper. This is a joint work with Enrico. He's a postdoc at Ohio State. Gaia is a PhD student at LSE, and Mara Squicciarini, she's my supervisor at Bocconi. And in this work, we're going to talk about religiosity and science. And in particular, we will focus on one precise episode, an historical episode, in fact, which was the Great Influenza pandemic in the United States. So we will focus on these two aspects of the social world, if you want, which are religion and innovation. So on the one hand, it is very well known that innovation is, well, probably the key driver of long-run growth, and has been, as such, thoroughly studied. Religion, in turn, is a fundamental aspect of culture, which has received increasing attention in recent years and has been shown to correlate with a number of dimensions which are economically relevant, such as, for instance, risk aversion and patience and trust. However, we will look at their interaction and their coevolution over time following a recent literature pioneered by Roland Benabou and co-authors, which postulates, documents that religion and science are negatively correlated. Now, you may not be overly surprised by this, even if you did not know this literature, as we can think of a number of historical episodes in which religion and science have been clashing. You can think, for instance, about the Galileo trial, but also about the fate of Darwinian biology and evolutionary biology, and the way the church opposed it. However, these arguments have only recently been formalized in these papers, which document that there is in fact a robustly negative correlation between religiosity and science over time and across space. But then we look at the contemporary world, and in particular, we look at the COVID crisis, and we're faced with a puzzle, an empirical puzzle from this perspective. And that's because we have quantitative evidence suggesting that the COVID outbreak ushered a positive effect on religiosity. In fact, religiosity increased in areas which were more exposed to the COVID pandemic, as shown by Janet Benson in a recent paper. But then we have also anecdotal evidence suggesting that, in fact, COVID fostered innovation efforts. You can think in particular about vaccines and the quick development of vaccines. Now, this would suggest, in principle, that there is a sort of positive correlation between religion and science in the aftermath of COVID, which is surprising in the face of this literature I was talking before about. So this is where this paper comes in. And the question that we asked, in a narrow sense, is how do pandemics impact religiosity and science, both separately and jointly? But then in a broader sense, if you want, we want to study if and how these two variables can synchronize and co-evolve over time. Let me give you a little bit of the setting and the preview of the results of the paper. We will be studying the period between 1900 and 1930 in the United States. And we will exploit as a source of exogenous variation the great influenza pandemic, which hit the US and the entire world just after, during and after the First World War, so between 1918 and 1920. We will be using new data on the universe of US patents. These have been digitized by Enrico, and they cover, and then they were collected from original patent documents. And then we will develop a new measure of revealed religiosity, which is based on naming patterns. And this is the methodological contribution of this paper. That is, we propose this new measure, which allows us to measure religiosity at a very granular level of spatial aggregation and high frequency in time. I will be moving on 2 layers of the analysis. And the first, in the first part of the presentation, I will be presenting a county level evidence. And I will show how innovation and religiosity reacted to the great influenza pandemic over 30 years. So we think of 30 years as a medium run kind of effect. And then we will document a puzzle, which we will try to unveil using more granular data at the household level. And this will allow us to reconcile our puzzling aggregate findings with the literature. So let me be a little bit more specific in terms of the findings that that we put forward in the paper. As I was saying in the first part of the analysis, we look at counties. And what we show is that in the short and medium run, counties which are more exposed to the influenza pandemic become more religious. So this large shock exerted a positive impact on religiosity, and we find that this is mainly driven by an increased intensity in Catholicism. And then we find that the pandemic fostered innovation in counties that are particularly hit. And in particular, we find that this effect is driven by an increase in pharmaceutical patents. Now, we will not speculate a lot on why this may have happened. I will briefly discuss 2 possible explanations for this, but still we find it somewhat interesting that the pandemic did not only foster an increase in innovation, but in fact, it directed innovation towards something which was arguably more in line with what the pandemic would have required. These are 2 novel effects of the great influenza pandemic that we document, but they do not tell us almost anything about how the 2 variables that we study, so religiosity and science, co-evolve over time. And this is where the 3rd piece of evidence that we document comes in. In particular, in this graph, I'm showing on the y-axis our measure of innovation, which is patents per capita, and on the x-axis, our measure of religiosity. I will explain in some minutes how we compute this. But if you buy that it is actually measuring religiosity, then we are showing that there is a negative and robust correlation between the 2 variables. And this is exactly what we would expect from the Benabou et al. Papers. This is computed using data before the pandemic, so between 1900 and 1917. But then if we plot the same relationship after the pandemic, we find exactly the opposite. So we find that the correlation flips from negative to positive. And this is puzzling from the perspective of the literature, because we would really expect the opposite. That is what we find before the pandemic. And this is the puzzle I was talking before about. The way we try to explain this puzzle is by looking at more granular data. So to talk about the mechanism, we will move at households, to look at households. And we will define scientifically inclined households as those that work in scientific occupations. Why we want to look at them? We want to look at them because these are the upper tail of the human capital distribution. So these are the ones that matter for the production of innovation. And what we find is that those more scientific households, become less religious after the pandemic in counties that are more hit. So this is a behavior that is opposed to that we find in the aggregate. So what we find is that the broad population overall becomes more religious, but the science-inclined population becomes less religious. And because these are the ones that matter for the production of science, what we show is that looking at this subsample of the population, we retrieve the negative correlation between religiosity and science, which we would expect from the literature. And this is the way we reconcile, we believe, our aggregate evidence with the papers by Benabou and other authors. Overall, these results would suggest evidence of a polarization of religious beliefs after the pandemic. And in particular, although I will not speculate a lot on this, we have two sources of coping mechanism against this sort of distress induced by the pandemic. One would be a religious coping mechanism, as studied by the psychology literature, which would be that individuals, when they are faced by economic and social distress, they turn to religion as a sort of coping device. The other one would be a sort of science coping mechanism, which is enacted by already scientifically inclined individuals, which are pushed towards more trust in science. We contributed 3 strands of literature in this paper. The first one is the one which studies the economics of religion. This is a fairly varied one, whose origin you can trace back to Max Weber, for instance. But more specifically, we will be talking to the substream of the literature which studies the interaction between religiosity and science. And what we do is we provide evidence of the fact that science and religiosity can positively co-evolve over time. But then we also uncover how this can happen with our household level analysis. We talk to the literature which studies how disasters impact innovation. This is there's a famous paper by Nathan Rosenberg, who argues that disasters act as focusing devices for direct innovation towards more salient areas, so to speak. And there is a recent literature which has provided evidence of this proposed mechanism. And what we do is we basically provide supporting evidence of this idea, and we show that the great influenza pandemic altered the direction of innovation towards pharmaceutical patents. And then, of course, we contribute to the literature which studies the economics of the Spanish flu. And as you can imagine, this has been blossoming after the COVID-19 pandemic. And we document 2 novel consequences of the flu. One is that it increased the religiosity, and the other is that it increased the innovation. So I will now move to the rest of the presentation. If there are questions, I'm super happy to take them. Otherwise, I will continue. Okay, so sorry, Bernat?
Well, yeah, I have a question.
Yeah.
I hope you can hear me. I don't get whether you're speaking about causality or correlation when explaining religiosity and science, sorry.
Yeah, so thanks a lot. So I will be talking about causality when I speak about the effects of the pandemic on innovation and on religiosity separately. So we will be able to provide evidence in a difference in difference setting about these separate effects. I will not claim causality in terms of the joint effect on religiosity and science. But still, we do provide suggestive evidence that the pandemic, in fact, causally flipped the relationship between the two. Although I will not be overly demanding, let's say, on that.
Okay, and the other question regarding the literature.
Yep.
So they spoke about correlation in these graphs, or they also try to speak about causality? Because I'm not sure about what we are speaking in the literature, I mean.
So you're talking about the one that studies the economics of religion and the correlation between religiosity and innovation.
Yeah,
I
exactly.
suppose. Yeah. This is a fairly new literature. In fact, we only have, I would say, 3 papers on this. And they all speak in terms of correlation. So the paper by Benabu is really a theoretical one. So they start from documenting cross-sectional correlation, basically, and they then build a model. They don't have any causal evidence on that.
Okay, thank you.
You're welcome.
Sorry, I have another question about that.
Yeah, sure.
But what is, maybe I missed that, but what is the mechanism you are like suggesting, which is behind the impact of religiosity on innovation, first of all, and second of all is you are mixing, or you are talking the same time about science and innovation, and they are not necessarily the same, right? Because there might be some science that is never transformed into innovation, in particular never transformed into patents, and the other way around too. So
yeah, totally.
So and are you looking at the specific innovations that you may claim that are like science, or how do you do that? Thanks.
Yeah, so thanks a lot. These are 2 excellent points. So in terms of the mechanism, so of course we cannot disentangle psychological mechanisms, so to speak. So what we do is we show that at a more granular level, people that were more scientifically inclined, which were less religious to start with, become even less religious. So this fact that this juxtaposition between the aggregate level evidence and the individual level evidence would suggest a form of ecological fallacy in our aggregate results. And in particular, it is not that what we would find is that it is not the same people who are becoming more religious and more innovative. These are 2 separate groups within the same counties. So this is our way to disentangle too. In terms of measurement, I fully agree that innovation and science are not the same thing. In particular, we will be proxying innovation with patents, as imperfect as it may be. We are following the literature on this, and basically everybody proxies science with innovation. You are very correct in saying that the 2 are not literally the same thing, but we still think that the 2 are positively correlated, so to speak. So it's an open question, I would say, in the literature, but we are following the gold standard here. Okay. So I will now probably go forward. I will be talking about the historical background a little bit, and then I will present the data and the methodological contribution that we have in the paper, and then I'll finally present the main results and the mechanism that we propose. So we study a big shock, which was the great influenza pandemic. So this was the deadliest pandemic in history, maybe after COVID. Now we're still not sure about this, but think about the fact that in 1920 the world population was about 2 billion people. 1 in 4, so 500 million people got infected from the influenza, and 50 million people died. So this was a major blow to mortality overall. Now, a fun fact, let's say, which many of you may know, is that the great influenza pandemic is known as Spanish flu to many people, and this is actually a misnomer, and that's because warring countries during World War I did not allow the press to report data on deaths, and so there was this misconceived idea that Spain was being overly hit by the pandemic just because the news in Spain, which was neutral, could report data on deaths. And then another key aspect of the influenza is that, unlike most infectious diseases, it was chiefly lethal for young males. Now, many people have highlighted that there are many similarities between the COVID-19 pandemic and the Great Influenza pandemic. Now, this may very well be true, but there were also important differences. For once, no cure nor vaccine was ever developed against the pandemic, and in fact, it ended when it became endemic. Its origin is still debated, but it probably originated in Kansas, and it spread through movements of soldiers during World War I, and also thanks to the fact that governments were unwilling to take containment measures during World War I and after, during the so-called Red Scare period. We will be looking at the US more precisely, and the US was one of the most severely hit Western countries. 1 in 4 people in the US got infected in 2 years, and about 0.7% of the population died. Now, to give you a comparison with the COVID, during the COVID-19 pandemic, 0.32% of the population died so far, which means that the Spanish flu was more than twice as deadly in per capita terms, let's say, than the COVID-19 pandemic. And just as another figure you may be interested in is that in the first year after the pandemic, life expectancy dropped by 12 years. So this was really a major hit on mortality in this period. There is some qualitative historical evidence suggesting that the mortality due to the flu was random. We will be not relying, of course, on these historical accounts for our identification, but still we find it reassuring that historians could not identify any systematic patterns of mortality across counties and states. We'll be talking about the religiosity and innovation / science, and we have some historical evidence suggesting that the pandemic, in fact, impacted these two dimensions. We know that spiritualism gained momentum after 1918. Now, whether this is due to World War I or the flu is open to questions. Phillips argues that this was really driven by the pandemic, but still this is anecdotal evidence. And some denominations openly demanded prayers for the pandemic, which was viewed as a manifestation of divine anger. And overall, we find that we know that the number of denominations in the US reached an all-time peak after the end of the pandemic. We also know that from qualitative, let's say, sources, that the pandemic had a positive impact on medical sciences. It overall led to an increased trust in science, and medicine became more scientific, so to speak, in that a number of developments were manifested after it ended. So even though there was no cure for the pandemic nor vaccine, a number of vaccines were developed in the early 1920s. Think about pertussis, TBC, or tetanus. Antibiotics, so a path-breaking discovery in medical sciences, were developed in 1928, and virology itself became a thing in the early 1930s, although viruses were already known. So this is a newspaper from 1918, and this is just to show you how important influenza was in the US. So the very centerpiece of the page is covered by the influenza, whereas news about the war were much less central, let's say. So let me now move to the data and empirical strategy that we employ in the paper. So we have to measure 3 things, basically. One is mortality due to the flu. The other is religiosity, and the third one is innovation, is science. Out of the 3, the simplest one to measure is mortality, and that's because we have data on mortality statistics gathered by the Bureau of Census, The collection began in the early 1900s, but coverage becomes substantive in 1915. And they cover 30 states, or about 80% of the US population. So we know for every county the number of deaths every year. Then for some counties at the city level, we also know the cause of death, but we follow the literature and which states that it's difficult to actually measure, to impute the cause of deaths. So we follow Beach and co-authors and measure deaths due to the Spanish flu as just the ratio between deaths during the flu and deaths after the flu. So this would be a sort of an excess deaths, which we impute to the pandemic. And then we code a binary measure, which is just 1 if the continuous measure is above its median and 0 otherwise. As a preliminary point, you may be worried that we are actually only capturing an effect due to World War I. And that's because, of course, the pandemic was reached its peak just after World War I. But then we find that deaths due to the pandemic are not correlated with deaths due to World War I at all. And here we are showing the spatial variation in the death rate across US counties. And as we see, there is quite a substantial variation across counties. And you can also see that the West tends to be highly exposed to the shock. So what we do is we just run a robustness test where we drop everything in the West and show that the results carry nonetheless. So the main challenge here is measuring religiosity. And that's because we don't have high frequency data on religiosity. This is true historically, of course, but it's true also nowadays. So basically, the literature measures religiosity using world value survey data, but world value survey data are available only at world value survey waves, which are pretty distant in time. So this is a data limitation that is true even nowadays. So what we do is we postulate that names carry some informational content on religiosity of parents. And the idea is that if you give more religious names to your kid, then you're more likely to be more religious yourself. And so what we do is we exploit this informational content to measure the revealed religiosity of parents. And if you buy this idea, then we can build a high frequency indicator of religiosity, which is also very granular because we can look at the religiosity of parents. And then we can also aggregate them up at, for instance, counties. We are not the first one to use names as sources of information, so to speak. This is a fairly established practice in psychology and sociology. It's more recent in econ, where names have been used to measure ethnicity, but also moral values and socioeconomic status. There is a recent paper by Anderson and Benson where they use names to infer religiosity. So our indicator is very much related to theirs, although then the definition of it is very much different. So let me describe you how we build our novel indicator. We start from a source of information, which is the census of religious bodies, which basically gives us at the county level every 10 years between 1906 and 1936, the number of people affiliated with any religious denomination. And we use it, we label it as measured religiosity. Then we use the US full count census, which has information on everybody that lives in the US over this period. And what we do is we compute name cohort frequencies of relative frequencies of names by cohort. This would basically, so what we do is for every cohort, we compute the ratio between the number of babies born with a particular name over the number of babies born overall in that cohort. And these are just, we call them name frequencies. And then we estimate the following regression, where on the left-hand side, we have measured religiosity from the census of religious bodies. And on the right-hand side, we have the name frequencies. Now, the rationale of the regression is very simple. And the idea is that more religious names are likely to be more common in more religious places. So the estimated coefficient delta here will give us the religiosity score of every name that we keep in the sample. Given those religiosity scores, what we can do is we can measure individual religiosity based on the names that they attach to their kids, but also county religiosity if we aggregate cohorts of newborn babies at the county level. And we do that for the entire 1900-1930 period. So in this figure, we are showing the estimated religiosity scores. And what we find is that names which we typically think of as being religious, such as James, John, Thomas, Joseph, and Paul, so biblical ones, all get attached to positive religiosity scores. And on the other hand, names which we typically do not think of as being religious, such as Margaret, William, Arthur, and in general, names that are derived from the Germanic tradition, if you want, are not attached. Are attached to negative religiosity scores. So this overall confirms our a priori guess on which would be the more religious names and which would not. Mary, I think, represents an instructive example of our methodology, because Mary is obviously a religious name, but in fact, Mary is so popular among everybody that it is not differentially popular among religious vis-a-vis non-religious people. So the distribution of Marys is not informative of the religiosity of parents. So we can repeat this exercise across different denominations. So in our working examples, we will be using Catholics and Protestants as the two major groups in the US population at the time. So having said that, the only thing that we still miss is how to measure science. So we will be proxying science with innovation, as the literature suggests we should do, and in turn we proxy innovation with patents, even though we all know that this may have some issues, so to speak. Although in this period, the patenting rate was already quite high. So we use this data, which were collected by Enrico during his PhD. These cover the universe of US patents between 1836 and nowadays. Enrico extracted information from OCR of original patent documents, and we have a number of data on patents. We have in particular the full distribution of technological classes, the geocoded inventor location, and the filing year of the patent. So we use innovation to measure science at the county level. And then we also need a variable which allows us to measure science at the individual level. This is trickier, of course, so we will have an imperfect measure of it. And in particular, we will be labeling individuals as being more science inclined if they are employed in a STEM occupation, STEM being science, technology, engineering, and mathematics. With the idea that if you're employed in a STEM occupation, then you're likely to have received scientific knowledge and education, and therefore you're likely to be more inclined towards science. And moreover, there is evidence that the presence of STEM people is conducive of economic development. So this is just a picture of a patent in 1897, and the red boxes tell us where the information that we use comes from in the raw text. The empirical strategy will be very simple. We will be estimating a number of flexible diff-in-diff, two-way fixed effect diff-in-diffs, where we have an outcome variable measured at the county year level. And we include, besides the two-way fixed effects, so we include an interaction between our measure of excess deaths and time indicators. So the set of delta coefficients will give us dynamic treatment effects of the flu on the outcome Y. The setting is simple in the sense that there is one treatment period, and everybody receives this, and every unit, so every county in this case, receives the treatment at the same period. So the Callaway and Santana critique does not apply, and being treated is an absorbing state, meaning that once counties are treated, they stay treated overall, throughout. We have an issue of continuous treatment because the excess deaths is of course continuous, but we call a binary exposure to the pandemic variable to correct for this possible bias and show that all results are consistent. So let me finally move to the empirical results that we have. So the first result that we document is that counties that are more exposed to the pandemic become more religious. The effect is found to be persistent and increasing over time, and there is no evidence that it dies out even after 10 years after the pandemic, with no evidence of pre-trend. So what we are showing here is that the pandemic fostered religiosity. Now, is this new? Yes, we did not know this before. Is this surprising? Not really, in the sense that there is a literature which is based on the religious coping hypothesis from psychology, which says that individuals, when faced with distress, socioeconomic distress, tend to turn to faith as a coping mechanism. And so what we are showing is evidence supporting this idea in this particular context. But then we also ask whether there is heterogeneity across denominations. And in particular, we re-estimate the diff for Protestants and Catholics, and we find that there is a sharp heterogeneity across the two denominations. And in particular, we find that the effect is driven solely by Catholics, with no effect from Protestants. Now, once more, this is not surprising. Janet Benson shows that after the COVID-19 pandemic, there was a general increase in religiosity, which was actually driven only by Catholics and Muslims, whereas Protestants did not react as much to the pandemic shock. And this is also in line with the psychology literature, which suggests that Catholicism is probably a quote-unquote better coping religion than Protestants for these kinds of unanticipated shocks. The second finding that we document is that counties which are more exposed to the pandemic become more innovative. So here the outcome variable is the number of patents overall. And with no evidence of pre-trend, we show that those counties which are more exposed, in countries that become more exposed, that the number of patents sharply increases after the pandemic, and the increase is somewhat growing, but definitely persistent over time. And this is a novel effect of the pandemic that we document. Now, as I was saying before, we explore heterogeneity across technological fields. So what we do is we re-estimate this diff in diff across different MBR fields. And here I'm showing the results for the pharmaceutical patents, which are drugs and chemical patents together, which are very highly collinear. So we collapse them to a single class. And we find that there is a positive and persistent increase in the production of pharmaceutical patents. But if we show the results for other classes, we find basically no evidence of an effect. So the pandemic had a positive impact on the production of pharmaceutical patents, but no impact whatsoever on any other field. As I was saying before, we can speculate on why this would be the case. We have a follow-up paper in which we're trying to disentangle possible explanations for this. One may think of a demand side effect, whereby the pandemic increased demand for innovation in pharmaceuticals. But you can also think of a supply side effect, and this would be more in line, more of a behavioral idea, so to speak, whereby individuals would be more inclined to invent in pharmaceuticals because the pandemic made it more salient that innovation in those fields was necessary. And this is somewhat more in line with Nathan Rosenberg's original idea. Although from this evidence, we cannot disentangle any of this.
Sorry, David, I have a question. Yeah, maybe, or I don't know. Yeah, there was any change in regulation in the US, for instance, to make easier to patent a new drug or a new medicine after the pandemic, and this may explain why there is this increase in the number of patents. I don't know.
So thank you. So if there was such a change in policy, then we would not expect. I'm not sure it would lead to this result, because here we're finding that here we're leveraging variation in exposure to the pandemic, right? So this would be a nationwide change in regulation. So we would not expect it to have a differential impact on counties that were more hit by the pandemic. That said, there was no such change in regulation. A concern that we had is that there was just fake science. So there is some evidence of sort of fake innovation after the pandemic. So people inventing these random devices which they claim to be super effective against the pandemic. In fact, what we do is we use a quality indicator from paper by Kelly in AR Insights. And we find that, in fact, also the quality of pharmaceutical patents increased in countries that are more hit by the pandemic. So overall, we do not find evidence of this production of fake innovation following the pandemic. But thanks, this was a plausible concern. So overall, so now up to now, I've been talking about the separate effects of religiosity of the pandemic on religiosity and science. And you may wonder, well, okay, fine, but this is all interesting and stuff, but how is this informative of the basic question from which you started? That is, how the two are correlated. So as I was saying before, we will not be providing causal evidence on these. What we show is that, and this is the same graph that I showed you at the beginning of the presentation, what we show is that before the Spanish flu, there is a robustly negative correlation between innovation and religiosity. And this correlation flips to being starkly positive after the pandemic. Now, the left-hand panel is fully in line with the literature. The right-hand panel is not. And so what we do is we go to more granular data to try to understand what is really going on in this setting. We do a number of robustness tests. They are not really interesting, so I will probably skip them, but if you're interested, we can discuss it later. So, as I was saying before, we find the aggregate analysis, we find a puzzling coevolution between religion and science. And we want to try to understand how can we explain that in the light of the literature. So what we do is we move the analysis towards a more granular layer, that is households. What we do is we assigned an indicator of religiosity to every household based on how they name their kids. So the sample will be the universe of households who had kids before and after the flu. And in any case, between 1900 and 1930. So why we want to condition on having kids before and after is because we want to observe the same household and assign to it a time varying indicator of religiosity before and after our shock. Then we have to define an indicator of science at the individual level, well, at the household level. So as I was saying before, what we do is we classify occupations into STEM and non-STEM, and we postulate that individuals at households which are that are employed in STEM occupations are themselves more science inclined, and that's because they received an education which made it possible for them to access these STEM occupations. So basically, in a nutshell, our results are as follows. We find that in counties that are more exposed to the influenza pandemic, scientific households become less religious compared to the rest of the population. And this is starkly opposed dynamics relative to our aggregate findings. And then, although I will not have time to discuss this today, we also find that the pandemic ushered an increase in the polarization of religious beliefs. So individuals that were less religious to start with become even less religious, and individuals which were more religious to start with become even more religious. Let's move to the first proposition that I had. So basically, what we want to do is we want to test how scientific households behave after the pandemic, and to do that we use a double difference. We estimate a double differences model, where we condition the sample on being into STEM occupations. So what we are comparing here is STEM people in counties leveraging variation in exposure to the flu pandemic across counties. And now we estimate also a more demanding triple differences model, where we compare STEM people and non-STEM people by exposure to the flu pandemic. So basically, what changes between these two models is the control group. In the first one is STEM people in non-exposed counties, whereas in the second one is non-STEM people in non-exposed counties. As a matter of fact, this does not matter that much. So here we are showing the results of these, the estimates of these models. So the first two columns show the results of the double diff, whereas the third and fourth column show the results of the triple diff. What we find is that STEM people become less religious in more exposed areas, and this is robust, including a battery of household level fixed effects, which are clearly extremely demanding in this setting. So what we find is that these scientific households behave in a sizably different manner relative to the broader population. In particular, if you recall, we find that the aggregate population becomes more religious, but then, and this is clearly opposed to what happens to the scientific population, so the STEM population. Now, the STEM populations has been shown to be the one that matters for the production of science overall. So the way we interpret these findings is that they allow us to reconcile the puzzle that we find in the aggregate with the literature. And in particular, that's because looking at the specific subsample of STEM people, which are the ones that matter for science, we are able to recover the negative correlation between religion and science, which we would expect ex ante. And so this allows us to reconcile our puzzling evidence at the county level with papers by Benabou and other authors. So this would be it. I would conclude now, and I'm more happy to take questions after it if there's any. What we did in this paper was to study the relationship between religiosity and science in the aftermath of a big shock, that is the Great Influenza pandemic. This relationship is generally thought of as being negative. And in fact, we do find a negative correlation between these two variables before the pandemic. But then we uncovered this empirical puzzle. That is, after the shock, counties that are more hit by the pandemic become both more religious and more innovative. And overall, this implies that the correlation between the two flips from negative to positive. So we are faced with this puzzle, and we have to try to understand how this talks to the literature. And to do that, we move to a more granular analysis at the individual level. And what we find is that science-inclined individuals actually become less religious. And this is clearly opposed to what happens to the rest of the population. So overall, by looking at science-inclined individuals, we recover this negative correlation between religion and science, and we also shed light on the mechanism in as much as we show that our aggregate puzzle is in fact an instance of an ecological fallacy, whereby it is not the same people in countries that are more hit by the pandemic which become both more religious and more innovative. These are really two separate groups, and in turn, this interpretation suggests that there are really two different ways to cope with this source of disasters. One being turning to religion, as the classic religious coping hypothesis would suggest. The other one being turning to science, as science-inclined individuals seem to behave according to. So this will be it. And thank you for your patience. And in case there are questions, I'm happy to take them.
Thank you, Davide. Thank you very much for this presentation. It's very interesting. I don't know if there are questions from the audience. Yeah, Vicente. Yeah.
I do the classical raise hand. So just raising my hand. Thank you very much, Davide. It was a very nice paper and presentation. Of course, I have some comments or doubts. My first doubt is about thinking on the other way around mechanism. So let's say you are a very religious family and you don't care for the flu, you trust on God, and then because of this, you have more deaths, let's say. First, you have more children, and because you have more children and the flu is affecting more children, it's likely that you are more affected. So maybe the mechanism is the other way around. So more religious families, you have more deaths. So this can be happening. I cannot imagine the other mechanism for let's say patents. I have no idea for this. Sorry. Okay, but this is one thing that I have in my mind. The other thing I'm wondering, it's about confounding mechanisms at that time in the US. And as you were talking, I was Googling Wikipedia about the Volstead Act, La Ley Seca. Okay, so you could not drink for a while, and then of course people drank, and then you have Al Capone and all these mafias and all these stories. Good. So the story at that point is, okay, there are other situations that could be affecting religiosity or some other issues that are at the same time, at the same period. So the Volstead Act started in 2020, but the process just became much a little bit earlier. And I think you have some heterogeneity in space that maybe you can look at, just at least to discard this, because I was reading that a list of states voted against it. So let's say you have some states which are more oriented just to prohibition of alcohol, while some other states were more, okay, let's not prohibit it. So you have some, maybe you have some heterogeneity in the parameters governing the relationship you are working with, okay? Maybe you could do some robustness checks for just separating the counties in one state against another's, and maybe you can discard this type of confounding factors behind your associations. As for the science, maybe Georgios or some just innovation-oriented people, they can say a little bit more, because for me it's a little bit weird just to think on patents and more influence of that. One thing that could be in this association could be the influence of urbanization. Cities at that time, many places were not the more healthy places. And in cities is where you have more science and more innovation. So maybe controlling for urbanization in the counties, maybe could be also interesting. And that's it. Thank you. It was very interesting. Thank you very much.
Thanks a lot for your points. I have some comments on that. So the fertility point is super relevant, of course, and it is so relevant that we have like 3 or 4 robustness tests for it. So we weighed households by the number of children they had before the pandemic, and also after it. We only include the firstborn, or we drop families with more than 3 kids to control for this sort of differential fertility across groups. And we find that the results are basically unchanged. Somewhat, they're even stronger in some specifications. So I don't think that that fertility, although plausible, can qualify, let's say, as an explanatory mechanism. In terms of heterogeneity, that makes total sense. So we have, of course, county fixed effects. We also include state by year fixed effects, which would probably like take a little bit more care of your concern there. In some robustness tests, although that's something we can do. We can do like a leave out estimation, dropping entire states, so to speak. But yeah, we can. I believe that we can do a lot on that side still. So we control for urbanization. In the regression, we include an urbanization times time indicator variable in the baseline regressions, and we do not find that results are sensitive to that. Of course, we can think of differential mortality rates in cities. So cities could, as you were saying, they were not like the healthiest place in the world in 1920. So there may be an effect on that. And so to rule that out, we use innovation in low density areas, say, as an outcome variable, and we still find effects. So yeah, I think that we can take care of that concern as well. But the heterogeneity part is totally plausible, and we can work more on that. Thank you.
And by the way, do you do any sort of trimming with the data? Because I guess that most of the patents are located in very specific places. I don't know if it could be affecting your results.
What do you mean exactly?
Just taking out of the regressions the 5 and top and bottom observations.
Yeah, sure. So the results that I showed you are on the full sample, but we also have robustness with the winsorization and at 2, 3, and 5% of the distribution of patents, and results are confirmed. And also you're taking the log of patents and this sort of standard, let's say, transformation of the data.
Great,
yeah.
Thank you.
Okay, I think Georgios have a question.
Can you hear me?
Yep.
Yes. Hello, David. Great paper.
Hi,
great
George.
work. Really enjoyed I really enjoyed the presentation. I have some comments and some doubts also. So you will be happy, I think, to address all of them. First of all, I missed a little bit of the background, which I think it is important, about how the parents name their children back in the 19th century US, because I don't know, I'm completely out of this, so I don't know how they used to name their children. I think this is important because based on that depends your religiosity measure, right? If I understand correctly, your approach. Because just to give you an example, in Greece at the moment, the name of the children follow in somehow the name of the grandfather or the grandfather of the father or of the mother. So for instance, my name is George and my grandfather was also George. But at the same time, my parents, only my father believes is a religious person. My mother is not. So based on that, your measure will have for instance, for a family that it is one out of two religious person, and just they name their children because they follow the tradition. I mean, there must be some measurement problem there, because in my case also it could be possible that both of my parents did not believe in religion. Actually, it's just they continue naming the children following the tradition of many years for that. So this is my first question. Now, moving to the thing that I think you received also questions about the science, how innovation, if can be innovation and science is the same thing. So now, this is just my opinion as an innovation guy, patent guy who works on that. But I'm just saying from the beginning that this is just my opinion at all. And I think that it is I think it's too far to proxy science to say that science and innovation are using patent data is the same thing. Of course, literature has shown that there is a strong correlation between patents and publications, or patents and knowledge production activities in general, but at the same time, there is correlation between, for instance, patents and GDP, but nobody says that patents is GDP when there is a literature review or something. So, for instance, if you have a very crappy patent, let's say it's just you want to protect it, or it's a defensive patent or something like this is not science at the same time. Or on the other way around, if you are not using any quality measures of innovation, so how you can?
No, we do.
You are using citations, I guess. In any case,
No.
I would be more easy to believe if you are using scientific words. Let's say you have the patent text of the patent. So for me, it will be easier to believe a story with scientific words in the patent text. But at the same time, I think I'm not sure, okay, for science and innovation, if you can say the same thing for both of them. It's just my opinion, but I say it's just my opinion. So feel free to drop it. And for me, the most interesting part of the story is the last part of the paper. So because the others, the others are also interesting, but for me, the micro level is really the most novel one, with the STEAM occupations and the households. And I don't know, for me, even if this was a paper by its own, it would be super fascinating for me, and contribute a lot, very significantly in the literature. I believe that the first part, because of the innovation science definition, can be criticized a lot. I was feeling more safe, more comfortable with the last part of the analysis, which is still very, very novel, and etc. So that's my comments. Thank you very much, David, again.
Yeah, thanks a lot. These are super valid points. Just want to comment a little bit. So you're right. We can add some information about the historical anecdotes on how people name their children. That said, there is I don't know exactly the subject of the that studies names, but we have looked quite a bit into papers on that. And there is anecdotal evidence again on this idea that in that period in the US, names were actually informative of religion. You're very correct in saying that the firstborn is usually named after the grandparent, and that's why in a robustness test we drop it. We drop the firstborn and also the two firstborn if they were of different genders. And all our results carry on. So I do not think that this is overly problematic, but still we can add some information on that. On how patents can proxy for science, so I agree. I'm not a super fan of this, but I guess that so there is this recent review of economic studies paper by Benabou and co-authors, which uses patents as a proxy for science, and so we're just following that, to be honest. That said, we are adjusting for quality indicators. In particular, we are repeating all our exercises using this quality measure developed by Kelly and co-authors. This is not citations because citations were not available in this period. They were not mandatory to report in 1920. And this is a text-based indicator of quality, and we find that all our results carry on with these quality adjustments. So I think that what you were saying, that is crappy patents, let's say, is not a critical concern for our analysis, given this adjustment. We could look at text, of course, that is all the way more demanding, but we can do that as well. Although, as I was saying before, this indicator by Kelly and co-authors is itself based on text, on the text of the patents, and in particular, it's based on novel words which are introduced in the patent and which are then used in subsequent ones. So overall, I think this goes in the direction you were pointing out. So the last part, so I agree, I fully agree, it's fascinating, although our indicator religiosity works better for relatively more aggregate, let's say, units such as counties. So I think that we have, I don't know, they both have advantages, I would say. So, but thanks for the comment.
Okay, are there more questions? Yes, Bernard.
Yeah, I have a question. Well, I don't know if you included that in the robustness checks because you skipped them. You only found effects on Catholics, right? Not on Protestants.
Yeah.
So as far as I know, Catholics in United States were mainly Irish American and Italian American. So it would be nice to look, I don't know how, but separately these two groups, because maybe you are capturing something which is related to only Irish American or only Italian American. So speaking about the confounding factors, well, there was the Irish war, like independence war at this time. So maybe they could change the behavior because they were very involved, the Irish American, in the Irish independence war, or something like this that could be related to these two groups. So maybe an additional robustness check could be trying to look separately those two groups. I don't know how, but that could be nice. And the other thing, well, this is more a comment than a question. It's that, well, I see that you don't have any policy recommendation, let's say, regarding these results. I understand, because I mean, it's not like very democratic to say that you have to change your religion or something like this. But so my point here is that I think it's kind of logical that any kind of ethical restriction, let's say, to science, so any kind of belief that you have, can be political or religiosity, will always reduce science, in the sense that any ethical constraint will, you know, somehow prevent you to do some things. I was thinking about vegans, for instance, that it's not a religion, but it's a belief. So they won't do experiments with animals, and that could harm somehow science, but it doesn't mean that it's bad itself. So, well, that could be also something to think about, that, you know, so having an ethical restriction can somehow reduce science production, but it's maybe can just change the way science is going. Mm-hmm. But that was only something that I was thinking now.
Yeah, thanks. Yeah, the point on immigrants, on immigrant group, ethnic group, actually, I should say, makes total sense. So we definitely can do some heterogeneity across ethnic groups. That said, it would challenge our results only if the presence of specific ethnic groups was correlated with the incidence of the flu. And we don't find that's the case. So we correlate the incidence of the flu with the presence of Italians, some Germans, of course, were also Catholics, French, which were few, Irish, and we don't find any significant correlation between those variables. So the presence of specific ethnic group is unlikely to be a major driver at all of our results. But that said, we can still look at it within county heterogeneity for these ethnic groups. For a second comment, yeah, I would need to be very cautious, let's say, but that's something we can expand on. Yeah, thanks.
Okay, thank you very much. Well, thank you, Davide, for accepting the invitation. It was a great presentation, very, very interesting. So
thanks a lot.
I stop here. So well, thank you everybody also for attending the seminar. Bye.
Bye bye.
Thank you.
Bye.
Bye.
Bye, George.